Okay, so we will start. So that this tutorial will be taken by Professor Prashant Pandey. Okay, let's start.
Am I visible?
Yeah.
So I hope I am visible. Huh? But I didn't see any response. Last time there was some response.
Yeah, visible, sir.
Huh? Yeah, maybe you can just switch it or somewhere else. Then, because I'm just worried that I'm visible or not. But we can see it here, right? Yeah, right. Now I can see my yes. Yeah. Okay, so very good. And I hope you are learning from a lot of very good people. So today, I will do one specific thing, couple of two things, work it out on the blackboard. Because you will see, you have not those things, like for example, teleportation, ODT, control flow teleportation. I work out that specific example because it's a very amazing application of this teleportation. It's an amazing application. And through that, you will learn a lot of things. I'll go slowly, step by step, because the formal aspects you know, but I implement those things step by step. So first of all, there are Alice and Bob. We name A and B, Alice and Bob. Now, these lines are called entangled chain. So it could be a singlet state, for example, this kind of thing. If minus, then the singlet plus is triplet. These two states occur in nature. For example, people have talked about, in chemistry. For example, if you look at hydrogen molecule or the helium, just like you are yesterday, the singlet, triplet usually occur in nature. Para-hydrogen, ortho-hydrogen, they are examples of that. But these other two, 0, 0, plus minus 1, 1 by 2, they are difficult to produce. Because why? Because in nature, usually you encounter, symmetry, like spherical symmetry, because of which, if these two electrons are pointing up, then the 0, 0, pointing down, 1, 1. 1 up, 1 down is the MZ or the azimuthal quantum number is 0. So in nature, because of spherical symmetry, these kind of things occur. So therefore, getting singlet triplet easy, but this object creates problems. People can artificially create them. And as has been told repeatedly, any two-level system can be thought of like this. So I will use any of them because you can actually convert one to the other by local transformations. You can check it yourself. For example, how do you go from 0, 0 plus 1, 1 to 0, 1, 1, 0? Just work it out. What do I local? What you do is, for example, what is 0, 0? 0 is 1, 0. 1 is equal to 0, 1. This object 0, 0. So we put work out by own hand. 1, 0 plus 1, 0. That is 1 times 1, 0. 0 times 1, 0. And that comes out as 1, 0, 0. Very good. So this is our entire channel. One is Alice, one is Bob, one is Alice, one is Bob. Now they meet together, create the entire state. Because to create entanglement, now people are coming up with methods to create remote locations. But typically, this non-local correlation, you have to come, create this thing, then physically go away. So, for example, typically where they have implemented, like the big chloroform molecule, so this object, Alice Bob, will be few angstroms away, big molecule. And now optical fibers, quite long distance across Danube. So those things are getting possible because optical fibers are able to preserve entanglement for longer distance. And as I told you, Professor Prem Kumar from Northwestern University has a great name in creating that kind of optical fibers. But anyway, so this is the state. Alice Bob. What they want to do? Alice want to send some information to Bob. Typically, we use unknown state, teleportation, alpha 0 or beta 1. So psi is an unknown state. Unknown state. Unknown state means what? I do not know what is alpha beta. It is alpha beta. If we expand this term, alpha 0 beta 1, this is called psi. Bracket rotation, alpha beta. This 0 and 1 is computational basis. Plus minus is Hadamard basis. So now state is unknown because I do not know what is alpha and beta. But state is normalized, so therefore alpha mod square beta mod equal 1. And alpha beta are complex numbers. So they will satisfy this current condition. Many times, for example, people take here, for example, you see, between these two, I have taken specific sign. So depends on your choice. Very good. So imagine alpha beta also are complex. So this is the state Alice has, unknown state. You will see after I work it out, you might have known by now that the state does not go. But at Bob's end, exactly same state is created using Bob's object 1 and one actually and one of the objects from here. Same state will be created when the information will go. Alpha beta is information. Alpha beta are complex numbers. This is an information. Because to complex number, we can that information goes. We will see how it goes. And the state is created. But physically, this 0 and 1 they don't go to our side. So let us see what happens. So it makes use of all the things what we have learned so far. Namely, state is unknown, and as you know, there are theorems that unknown state cannot be xeroxed or cannot be created on the other side. So this was clearly worked out for you. Like Professor Puri, Aditi also pointed out, unknown state you cannot copy. So very good. So now we don't want to copy, we want to teleport. So what is happening in teleport? So this state is with Alice. Alice physically could be somewhere like in Delhi, Bob would be working far away. So first what they will do, let me show you mathematically, and then for their end they will do only experiment. Experiment will involve measurement and local unitary transformation. So the steps that are involved is local unitary transformation. That's it. Then measurement. First will be measurement. Second will be local. Second will be classical communication. We go through all the steps very carefully. Communication. And third will be local measurement. These three steps. So this is a communication protocol. We have to estimate how much cost we are having. So we have to estimate classical how much is telephone bill. That is classical communication. Entanglement, they have to meet and create. Money goes in creating that. So we have to compute entanglement cost. Because it is all money. Then classical communication cost. How much of classical communication telephone bill? Then we have to check is it deterministic or probabilistic. That means each time we are doing is really working out or it's not working out. Half of the time it works, half of the time doesn't work. So you hear these kind of languages. Deterministic or probability. Then humanity is working out.
Sir, can you use a headphone, please?
Yeah. What?
Sir, can you use a headphone, please? I think the room is big. That's why the sound is a little bit noisy.
Headphone. Yeah. Huh? पर YouTube में तो आवाज आ रहा है बोल रहे हैं. I don't have a headphone right now here with me. If I can speak more loudly if you want. Are you
Okay,
able
sir.
to- Huh?
Okay, sir, carry on.
Okay. So let me again repeat the step. There are two parties, Alice and Bob, located far away from each other physically, namely in the sense of space. Alice gets an unknown state psi. Unknown means alpha beta is not known to her. That state will be teleported to Bob. So from the outset, we say very clearly, teleportation does not mean the state will physically go. This information alpha beta, you will see, will go to Bob's side, and state will be recreated at Bob's side. So while doing this, it's a communication protocol. Teleportation is a communication protocol. We needed an entangled channel. You will see if it is not maximally entangled, namely, if it is not plus or minus, or if it is not singlet, triplet, 0, 1, plus minus 1, 0, 2, then it will not be deterministic. It will work out half of the time, other half will be there. So you will hear in communication protocol, people will be talking about is it deterministic or is it probabilistic? You put any number here, for example, some alpha. You find it will not be work out all the time. Half of the time it will work out, other half will not work. Then, after you will find out that when you are doing this thing, it will cost money. In what sense? Because to create entire state, you need an apparatus. Alice and Bobs will physically brought to the same place. So when you lose entanglement, it costs money. So quote and unquote, entanglement cost, you have to establish how much of entanglement cost my communication protocol takes to send, recreate an unknown state from one side to other. But in the process, you need classical communication. A telephone call has to be made. In how many units? That also has to be shown. And as I emphasize, let me repeat again. What kind of channel has to be chosen so that all the time is to work? You need to be deterministic. But typically, there is some noise. Then that's why you have to check. Has it, whenever it is working, has it gone exactly what it has gone? Fidelity. Fidelity in this word. So these are the words you will hear. And local unitary transfer and classical communication people combine. So to a what called LOCC, you must have seen it by now n number of times. Local unitary transformation and classical communication. Most of the quantum communication protocols uses local unitary transformation and classical communication. For example, you find out this is used to classify states. Is it good for communication or bad for communication? I mentioned to you about that also. Very good. So now, mathematically, all those words are there. So let me, what I did. So first, I just expand it. Nothing more, just expand it. So when it comes to, first thing you will see, I have to do measurement. So measurement, whenever there is a question of measurement, so you ask this kind of specific questions. That is the reason I want you, I'm going through it carefully. First point, which basis? Namely, first of all, is it one particle, two particle? If it is one particle or two particle, what is the basis? In case of one particle, for example, basis could be 0, 1, could be plus minus. Fortunately, in this case, it is not one particle, it is two particles. In two particles, for example, what is the basis? So, basis could be 1, 0, 0, computational basis, 0, 1, 0, 0, 0, 0, 1, 0, or 0, 0, 1, computational basis, or it could be Bell basis. So, in fact, we will be using Bell basis. 1 by root 2, 1, 0 plus minus 1, 1 by root 2, 0, 1 plus minus 1, 0. This is the basis which you use. In this language, the basis that is used is the bare basis, and in this language it will be 0, 0 plus minus 1, 1 by root 2, 0, 1 plus minus 1 divided by root 2. Okay. You will find out writing in this makes life more simple because matrix multiplication gives you huge big matrices. But if you write like this and draw electronic circuit, you can handle it. It is much easier. That I learned first time when I was doing these kind of things from and back. So very good. So Bell basis have been done. Two particle measurement, Bell basis have been specified. So then what you do? For example, just like we did when you want to measure a single particle, you ask which basis. You have to expand in terms of that basis. Suppose there is some testing, this I had done in the past class. I want to measure in this basis. What do? You go 0, expand it in terms of this basis. Plus, minus value. Then after measurement, which is given by this arrow, outcome will be either plus or minus, which is one probability. Why equal probability? 1 by 2. Square of that is 1/2. But a given measurement, this or that, completely arbitrary. So now, let us do the same thing. So Bell measurement has to be done between which particles? The one and this has, because it has a local measurement. So measurement is local because the apparatus cannot extend physically to between Alice and Bob. So it's a local measurement between 0 and this. So what I have to do? I have to write it in terms of Bell state. So let me do that because I remember. So there will be how many terms are here? 4 terms. Here if you expand, there are 4 terms. Now I will expand it in terms of 16 terms. But it's a mathematical identity that those 16 terms, if you add, they will be equal to these 4 terms. You work it out. Not very difficult. So it will be 0, 0. Which is 0? 0 of this unknown state and 0 of this. Was 0, sorry, 1, 1. And this, okay, plus minus by root 2 because of normalization. Now, Bob state will be alpha 0, Bob, plus minus beta 1, Bob. So, there will be another block 0, 1, plus minus 1, 0 by root 2. Alpha 1, it was 0, 1 here. Now it is alpha 1 Bob, plus minus beta 0 Bob. This was how I think it is correct. It's a matter of how many terms? 4 for this, 4 for the minus sign, 4 for this, 4 total 8, 16 terms. You just add them up. I think the factor is correct. You will cancel and you will get these 4 terms. It's an identity. So you may ask, why did I write, for example, in this way? Because I want to measure this basis. Basis is made out of unknown 0 and Alice. So I am expanding in terms of the complete orthogonal basis. Complete orthogonal basis. And you see, root 2 is normalization. Alpha 0 beta 1 is normalized. So this is a mathematical identity. So once I have done it, then you ask that after measurement, what will happen? You take some measurement like this arrow, what will happen? So we agreed out of these 4, any of them can be obtained by Alice. So there will be 4 choices. This or this, this or this. One measurement will lead to one of them arbitrary. If you do thousands of measurements, then you will get each of them 1/4 times this, 1/4 times the minus, 1/4 this, 1/4 that. Why? Because 1 by 2 factor. They are unit vectors. So now suppose outcome is the first one. After measurement, outcome is this. 1 Alice by root 2 alpha 0 Bob plus beta 1 Bob. So now You may ask, what happened with one arm? That you convince yourself because initially the state was normalized, the full state. Finally, this also normalized because this is normalized, this is also normalized. So half will be there. Now, in this case, you observe something very interesting. That initially, Alice and Bob were entangled because they were having the state. You know, that initial state was 0, 0, cross 1, 1, 5, 2, and Alice Bob. So Alice Bob were entangled. After the measurement, and this fellow psi was here. Psi was isolated. So it was a separable. This fellow is one, these two are entangled. And that is maximally entangled. So note it all. Maximally entangled. People may be wondering what is maximally entangled. I can explain to you later. What Bell states are maximally entangled. Many authors have used this word. So what happened is after the measurement in the Bell basis, this fellow is separable. This becomes this times this. So unknown state with Alice. Maximally entangled. What separated from the other flow? Maximally entangled. And times this flow separated. This is very interesting result. But first, what happened? Now you see, Alice knows that because Alice has known the mathematics, Alice knows that since he has got the state, she does not know the unknown state. What this mathematics tells her, whatever alpha beta, the state has been created at Bob's end. So she formally tells Bob, apply identity. So after measurement, the state at Bob is alpha beta and apply identity. That means 1, 0, 1, 0. So alpha beta, Bob. You see, the state has been recreated at Bob's end by measurement in Bell basis, local communication, and apply identity. And in the process, what has happened is a very beautiful application. Only engineers can think about it. I always admire that this fact that unknown state has gone to Alice Bob uses the first paper you see, Bennett and co-authors. They mention EPR correlation. EPR thing was used Einstein proposed to go and paradox and the paradox. So engineers used it. Same correlation they used for practical tasks. And information has gone unknown. Alice does not know. Alice doesn't open the practical file. Unknown information is guaranteed. State does not go. Okay. But if it succeeds, exactly alpha beta, no errors. Exact alpha beta from here goes to exact alpha beta, no errors. There is no classical algorithm which can do it. So therefore, and in the process, something very interesting has happened. That I'll talk to you later. This maximally entangled flow has separated. As if, two friends are so tightly bound. If another fellow tries to come in, the bond will break. So these two fellows get tightly bound and these two are separated. This was recognized as entanglement monogamy. We hear about this entanglement monogamy. As the word shows, monogamy means one marriage. So as if these two are maximally entangled, as if they are married forever, monogamous. You don't choose another one. So if another fellow tries to come in, then what happens is that marriage breaks. And these two get monogamy between them. So this word besides has been used. Again, authors, Kundu and others, 3 authors. This is a kind of quantum property which is very fascinating and it has also used. Some of the chemical bonds in some of the chemistry we find also this kind of property. I've seen in sitting some of the seminars, one particle gets attached here, the other particle gets out from the other channel. So this is a property of entanglement, maximally entanglement. You cannot push somebody else. Very good. Now, If this is minus, what will happen? We agree if it is minus, this will go minus. So what is the state now? The state now is alpha of n is minus. How do we correct it? Apply Z. So Alice will tell that now if it is minus, you apply at Bob, you apply local transformation for Z. Why local? Because it is only at Bob's state. So once you apply, state is correct. So very good. Now these two are done. Then how about the other two? Is the outcome. E 1 by root 2, 0 1 plus 1 0 5. So this is the state of Alice and the unknown state, and Bob is alpha 1 beta or Bob plus beta 0 Bob. The state is now beta. So what do we do? You apply. And if you tell Bob, you apply x. X is sigma x, right? Very good. Once you do that, that's alpha beta. Now then, if it is minus, this becomes minus. So it is, or this minus that plus, I don't remember, over or minus sign doesn't make any difference. Excuse me. So now, it is, let us say, beta, minus beta plus beta doesn't matter. Beta minus alpha. Then how do you get alpha beta? You apply 0 minus 1 1 0. Now what is this 0 minus 1 1 0? That is actually 0 minus I 0 is our Pauli matrix. If you multiply by minus I, you get this. So if you want I, then you have to make it over or minus I, doesn't make any difference. So if you apply this matrix, which is called Y, then Bob will get it. So in the process, now we found after the measurement, Bob can get the exact state after Alice communicates the local gates to be applied. So the gates that have been applied are I, okay, X, Y, and Z. So in polymetrics, sigma Z, sigma X, and this is for I and sigma Y. So how many information have been sent? 4, 1, 2, 3, 4. So 4 is written as 2 per square. The log with respect to base 2. How it is measured. So that is 2. So this is called 2 C bits of communication. 2 C bits of communication. That is how apparently whatever number you send, they will convert it to that. That is how they will charge you. 2 C bits of communication. Maybe that is how they are charging us now. So that is now. Now, then what has happened? Entanglement cost. So we had a entangled channel between these and Bob plus 1 1 by 2. Now that has been broken because what happened? That in the process, Alice gets entangled with unknown fellow and 1 1 Alice. Bob has decoupled. Bob, Alice, Bob has decoupled. So 1 unit of, and people have computed, you can easily compute that this state has 1 unit of entanglement. 1 unit of entanglement. So 1 unit of entanglement has been lost. So that money has to be paid. Because you have to bring them together, they are air, you have to create in the lab, so that amount you have to pay. So this is the point. But and this state is exact. So right now we are doing it for pure state. Pure state. So Whatever you got, because for the high, take the overlap, that is called fidelity. More square of that. So it's fidelity 1. And it is deterministic. Whatever is the outcome, if you apply ROCC, you get it. So fidelity 1 and deterministic. Alright. So then you may ask, can I give you an example where it will be probabilistic? Answer yes. That was a very nice paper of Professor Potki was overall Chai and Institute of Physics. They show that if you take non-maximal entire state, for example, work it out yourself. Take this to be here, normalization is this, here. Expand in the same way. Try to do teleportation. Okay. Let me call it A, so that doesn't get mixed up. You will find out half of the time it will work. Just take it out. Only half of the time. Other half, even when you're expanding, you find out you will be able to expand it 0 Alice plus minus 1 0 Alice by 2 alpha 0. Is it cross or there is some A will be there? Check it out. Maybe there is some A here. 1 plus x square or something. Okay. Alpha 0 plus beta 1 bob. This kind of thing will happen for 2 of them, other will not work out. Other, this thing will not work out, alpha beta will not be able to go. So the states will become, the other 2 states will be independent of alpha. You see, alpha beta should not appear in the state because that information should go there. Check it out. This is physics sector A paper, you can remember correctly. You can work it out yourself, very simple. The other 2 things will become dependent on alpha. So therefore, half of the time it will work, other half will not work. So it is probabilistic, not deterministic. Then I told you about fidelity. Then you go to mixed state. This is pure state. Mixed state also to work it out. For example, up to certain, if you look at entanglement, there is something called concurrence, which takes care of a mixed state. And if I remember correctly, there was a nice paper by Dr. Adhikari, what say he's right now in Delhi College of Engineering. Delhi College of Engineering. What to we put them? Anyway, check it out. There are people who have worked it out, mixed state teleportation. You find out that it will not work all the times because the environment has noise. Some of the time it will work. These are all routine exercises now. So therefore, what did we learn? That this teleportation can be done, but you have to do measurement in bare basis. As Aditi was pointing out that even now, you can create and nicely manipulate optically 2 states, not other 2. So how to realize this bare measurement using optical, linear optics is an open challenge. You can play around yourself. Read more about that. That's open question. Now, similarly, teleportation is monogamy. That how much of entanglement you need. You saw that if it is maximally entangled Alice and Bob, it will work out or it will not work out. Now, finally, what is happening? What is happening is that at the end, you have a channel matrices of this kind, some high AB. And finally, you want to do certain manipulation. You will have something like, let us say, some high leading AB, Alice 0, sorry. Alice and unknown state, let us call U, and side bomb or side relay bomb. That's what we want to do because Depending on the measurement, the state could be any of them. Right? So if you can identity, there will be 4 terms. So and there may be overall some normalization factor. We want to each case is the same thing, that 5 unknown state separable from this, right? So therefore, it's a matrix factorization problem. You can see if it is nothing but for example, the size of parameter. And this object is a 4 by 4 matrix. Right? What is phi AB? For example, it is, but in this case, for example, so it's a column vector, it's a column vector. And finally, for example, one of the cases would be a column vector between Alice and Bob. Now it will be 1, 0, 0, 1 between unknown state and Bob, Alice. And Bob is separate. So if you see, it's actually a operations which are, it's a matrix factorization. I see it in that way. Now, why is it that if the channel is maximally entangled, it works? Why it doesn't work if it's not maximally entangled? I still don't know. So, now people have also sort of tried to understand it in terms of information flow. That actually leads to some beautiful mathematics called category theory. Category theory. It does not only mathematically existed. People found interpretation of this through category theory. Apparently, it provides a very beautiful unifying language. Category theory. Right. This year you will find out. Mamta will be giving some talks on category theory. Last time we had several talks. Very, very nice book. So I have knowledge provided Bob Bouquet from Oxford, if I remember correctly the name. We give that exact reference from Oxford. So they have a nice book, full book on category theory and quantum information and quantum communication. So very deep mathematics involved, matrices, their factorization, and different branches of mathematics comes in. Similarly, to find out this maximally entangled state, that also people are trying to understand that what is the meaning of maximally entanglement. So in that context, how much time I have? How much time I have? 40 minutes. Okay, so I have time. Tell me whenever you are tired. Okay, so now maximally entangled. So again, working out by hand is very simple. And this, for example, Alice Bob 0, 0 plus 1, 1 by. So typically they will compute. First, they will take this fellow, find out this so-called reduced density matrix, and from there they will compute something called von Neumann entropy. So let us do that. So reduced density matrix. How do you compute? You take your full row. You first find out which party, with respect to which I will be doing this. For example, with Alice or Bob, doesn't matter. Again, ask what are the bases, and you have to take quote unquote projection with respect to that basis. So that will produce for you the reduced density matrix. That is left with reduced density matrix or not. So you can take any basis. You can do group by step by step, decide the basis, and take projection. Basically, trace. So more formally, you have to take row, I, some over. That becomes your reduced matrix. If R is 4, is summation into Alice, then you reduce matrix for Bob. So let us do it. Very difficult. 0, 0, cross 1, 1 by root 2. But reduced density matrix means density matrix is what? Size, sign. For example, it is pure, only one term. Only one term is pure. So I have to have same thing here also. This form plus 1, 1. And this form by root 2. And this is my whole density matrix. So 1 over root 2 comes out. Now I take first 0, 0. Sandwich between 0 from both these sides. What will happen? How many terms are here? There are 1, 2, 3, and 4. If I take 0, 0 from both the sides, 0, 0, only one term has. So these terms will contribute 0, 0, 0, 0, and the next term. This will contribute to 0, 0. All the others will be 0. So you convince yourself the only term that will survive because of orthogonality, others will be 0. And same is 0, others are 1. So the first term will give me 1 half 0, 0. Other term will give me 1 half 1. Now low and below, I have come up with a 2 by 2 matrix. How does it look? So 0, 0 is what? 1, I always like to mistake in this one. So this is equal to 1 times 1, 0 and 0 times 1, 0. A 2 by 2 matrix, so that becomes 1, 0, 0. So the other color becomes 0, 0, 0, 1. Becomes half 1, 1. Wow. So I am left with a reduced density matrix, which is identity. Identity means what? Now it's a mixed state. Why mixed? Because there are two terms. Whatever I do, I cannot make it one term. So it's mixed state. Rank is now 2. Okay. And it is maximally mixed. Why maximally mixed? Because identity. No preference. All the colors are identity. Maximally mixed. Mixed and maximal. Now how do I compute Van entropy? Entropy. So the formula is minus lambda I log lambda I. Minus lambda I log lambda I. So what are the lambdas? Lambda 1 is half, lambda 2 is half. So the entropy on the right? So minus 1 half log 1 half minus 1 half log 1 half. That is my entropy. And log 1 half. Everything I have to compute with respect to base 2. Remember that 4 was 2 square, log with respect to base 2 was 2. So here, and this becomes 1 half log of 2, another 1 half log of 2, because log 1 by 2, log 1 is 0, and log 1 by 2 is how much? Log 1 minus log 2. Log 1 is 0. So very good, and this is 1. The log 2 is the base 2. So it becomes half plus half equal to 1. So this is when 1 E bit of entanglement. And you compute, others will be less. Okay. So therefore, for example, to take this state 0, 0, plus A1. 1 plus A square. Now do the same thing here. So what will you find? You will find rho reduced. It will be 1 plus A square, I think that is square. So that will be this. This will be 1, 0, 0, A square. I think I'm correct. So trace of rho is 1. 1. For pure rho square is equal to rho, trace rho is 1. Probability is concerned. So trace rho reduced if I take 1 plus A square divided by 1 plus A square. So it is 1. Perfect density matrix diagonal. You can see they are no longer maximum width. So it is not maximum width. So okay, and
মানে এতে
are you guys clear or do I need to do it once more? Maximally and time state. Maximally and time state, you have to compute the density matrix. Density matrix, if it is identity, for example, in this case. Okay, so if it is anywhere, if it is 1, 1, 1, 1, something like that, maximally mixed. Everybody are 1. Then it will be like 1 over n kind of. 2 by 2 are 1. With light, we call it completely unpolarized light. Completely unpolarized light. So as I told you, look at that optics book or Markov, for example. Everywhere you find out in the polarization description, the pure states are the polarized states which are lying on the block sphere. Identity origin is completely non-polarized light. Rest are partially polarized light. So light optics people know it. So looks like if it is partially polarized, you can still do teleportation probabilistically half of the time. And amount, how much you quantify through this procedure. And it has to be reduced density matrix, has to be density matrix, trace rho has to be 1. Okay. Any more questions? Okay, very good. Now, so what the overall, that was a very nice result that non-maximally time states will teleport half the time, the probability. Another important result was by in this Chirac, Jolor, and I think there was one more author, I don't forget. They found out that these fellows, the so-called Greenberger, Born, and Jaina, all the big fellows, all of them are alive. Hopefully, the animals will get a Nobel Prize. Austria, you have seen his student did over Japan, in China, doing miraculous things, and he is well now active, very good. Austrian Science Foundation president, very nice person. I met him because I had gone there personally. He used to come to Dalai Lama every year for debate about science and religion. Greenberger was my teacher in City College. We used to sort of make fun of our teacher, just like you people do. Lot of hair, always, going around, foundation of quantum mechanics. Nobody was carrying those days. 82 is the year I am talking about. But, that is around that time they come up with the state. Form is the same form, CHHS identity. You remember this thing people are talking about? Inequality. same hall. They were all, according to Geilinger, those days, very difficult to get a job. So, he did his PhD in nuclear physics, nobody used to care. And then he had gone to City College, New York, where Harvard was also visiting. So they came up with this state. This state, if you see, is very similar to 0, 0 plus 1, 1 value. So initially people say, what is so big, adding 1 more 0? But you can check, read it yourself. That it has certain property, so-called stronger non-locality, which was not here. So they became famous, G and J. So you have to now come up with states, we should have something more. Now if I put 1 more, nobody will care. Right? If I put 1 something and don't say what new thing it has, nobody will care. But they showed there is something in it which was not here. Stronger non-locality. That is how the state carries their name. So now you have to decide which 3 of you or 4 of you want to give the state. So whose name comes first? So we decided then one used to go here. Typically name comes according to this letter. G, S, Z. Why I'm talking about name? Because Greenberger was of course my teacher. So he wrote a paper with his teacher. Very famous one, man. Name is O. W. Greenberger. Okay. So they wrote apparently a paper where it was told that a third paper is required. Third author is required. Although there was some problem. So what they did, they wrote a paper putting a fictitious name. Greenberger, and Greenbergest. Actually, it is true, you can check. So, find out about this episode. So, we heard about it when we were students and we used to make fun. Greenbergest. But those days, foundation was not taken very seriously. That was there. Feynman was talking about using quantum computer. People were not thinking seriously. But things changed, and because of computer source, factorization, and reverse source algorithm in 90s. But in 80s, ideas were there. Okay. So, same Greenberger. What this Jolor and Chirac and Guanine, they showed that 3 particles, there are 2 distinct classes. One is this class. How many of them will be there? 8 of them. Because 2 to 3 is 8. So 8 state vectors orthogonal to each other. If all putting plus minus, you get all of them. They belong to one class. They can teleport. Teleport with a jet. Teleport, yes. For this class, or W class, 1, 0, 0, minus 3, W square. Or W class. W. That authority. So from teleport perspective, nobody will buy them. So classes were defined according to their ability to teleport or not teleport. Now if you play around, just play around. You find out that put something like A, B, C, and normalize properly. Put them here, S square or B square or C square. If you do teleportation of single qubit, you find out this is for normalization. I'm taking the here. There has to be another condition. S square or B square equal to C square. Only then it will teleport. And plug it here. 2C square equal to 1. C equal to 1 by 2 plus minus. That is what Fortier and company found out. So they found out if this A, B, C are asymmetric, and then they root 2 kind of factor here, 1 by root 2 here or root 2 here, doesn't matter if you're all normalized. Namely this condition, if it is satisfied, then you can teleport. So then people found out that so if you see geometrically, it's like x square plus y square or x square equal to 1. What does it describe? It describes a sphere. Right. So x, y, z In addition, an additional condition. What is it? X square plus y square has to be Z square. Then only the equation will happen. Many of you have, very clever mind. So x square plus y square is equal to z square. Only those kind of meridians or one of those orbits here, they are only if you are there, you will take. You think about it geometrically. So why I am saying this? With entanglement, teleportation, all those things can be imagined in a very geometric way. And you can develop your own picture. So for example, our man who got a bit of disconnected from Azerbaijan, Kazakhstan, she was talking about state classification in terms of polymatrices. So many people try to understand entanglement in many different ways. Okay, so I will give you one more perspective, which I have used to understand it for myself. So when I saw this entangled state, maximally entangled state, then I was always wondering, what is so big deal about locus, just a column vector? I have seen them in terms of Dirac equation. But only when they are located in this way and with 1, they are maximally entangled. For example, if I put them 1 by 1, no entanglement. If I put them 1 by 3, for example, 1, 0, less entanglement. If I put 1, all 1, then no entanglement. So I was asking, it's actually true. Whoever I used to meet when I was in Ahmedabad, physical research laboratory, I used to ask students, what do you see so special about this? So people used to think, one boy, engineering guy, who is now settling in USA. So he had told me one day, around 4 o'clock in the night, that I had the answer. And his answer was that, look, consider the general case. Why are you so bothered about this location? Since you are asking a general question, suppose my state is A, B, C, D. I don't care about where they are. Now, if I want to check their entangled or not, so his procedure was make a matrix out of it. Matrix will be A, B, C, D. Make this, put it like that. His claim was that determinant of A, B, C, D, if you take the magnitude, that will tell you how much of entanglement is there or not there. So it is surprising. Let us check, is it really true? So I take this matrix 1, 0, 0, 1 by 1 by 2. So I follow his prescription, make a matrix of 1 by 2, 0, 0, 1. Take the determinant. Determinant is equal to half. And if I take -1, I have -1. Determinant will be -half. Take the magnitude to the half. Oh, that's correct. So now if I get the other state 1, 1, 1, 1. Matrix is 1/2, 1, 1, 1. Determinant is 0. Okay, so it is not entangled. Then I figure out it's not entangled because it is a product. Direct product of 1 over 2. But I don't have to check. I find determinant is non-zero, magnitude entangled. Now, what about this other two? 1 by 3, 1, 1, 1, 0. So now determinant comes out to be 1 by 3, 1, 1, 1, 0. So determinant should be 1. So it is actually less entangled. So several questions arise here. Right? Why is the determinant first of all giving me entanglement? Secondly, 2 terms maximally entangled. If I add 2 of them, then it is maximally entangled. But the moment I add 3, entanglement decreases. Cross 1 by root 3. 0, 1, 0, 0, cross 1 by root 3. 0, entanglement process. This is still not answered. How many terms superposition is you take in a general situation so that entanglement will become maximum? Not yet clear. Then the determinant. Why is determinant? Fortunately, there was a student from BSc through this NIMS program of Government of India, Vinith Bhaskar. So I asked him this question. He was very intrigued. He has a good mathematical brain. He was a good IIT Guwahati. Whenever he used to pass, he would come to Calcutta. We used to work, pursue the problem, and he finally showed that determinant is always area. Where did you come up with determinant? A cross B, right? Determinant. For example, A cross B, how do you compute? You take, for example, I, J, K, vectors A, X, A, Y, A, Z, B, X, B, Y, B, Z. So determinant just connects to area. Core, dot product and core product. So that is how finally he pointed out, create some new mathematics, and he taught me there is something called waste product. WE, DGM, waste product. Very similar to cross product. For example, A cross B. What is A cross B? A cross B, I as a component will be IJK. It will leave if it is A cross B, it has to go to the third direction. So people pointed out that no, everything you can do on the plane. So the cross product can be maintained something like A cross B. Something like that. By vectors. So this is a new development. Mathematics or geometrical algebra. In fact, we used it and we gave the physical reason why this thing happens. And it finally found out it has nothing to do, entanglement is simply vectors parallel or perpendicular. If they're parallel, convince yourself that people can check it out, published, subsequently, more general things have come out. In fact, very recently, if you go to the archive, you can check actually PPA Panangari. Google Scholar. This is where I keep track of my citation. You can check if you go to search year, starting from 2021, we have in fact very recent couple of papers we have shown that vectors being parallel or perpendicular. The key to understand entanglement, just vectors, nothing more than that. Not unexpected because finally they are all vector identities. So uncertainty, all these things for inequality can be applied here. And beautiful thing is this A where's B. Here we have to use an identity. That identity apparently Lagrange was the person according to whom this identity was there, Lagrange. Somewhat like your Schwarz inequality. But when you communicate a debate, one mathematician from MIT told us, look, this is not Lagrange only. You have your Lagrange cross Brahmagupta. I hope I'm spelling it correctly. So this identity, Brahmagupta knew it because of vectors used it in calculus now. Sun and moon system. So the identity, which are essentially some have like triangular inequality, is the one which we used and finally got answer for our entanglement. Completely in terms of parallel perpendicular nature. This thing, lot of things remains to be understood, particularly three, believe it or not, 3 particle, 4 particle, things are still not clear. What is the quantum correlation? Lot of quantum correlations people have found, something called quantum discord, coherence, variety of things are useful in variety of ways. Many things are not understood. So even for 2 particle case, for mixed case. So lot of work remains to be done, pure matrix property. You guys are young. I have found that young people do it faster than us. So you will come up with some good idea by looking at very simple things. Don't make your life complicated. So I think I'll stop here. What's the time now? Around 12:45. So I have on my 1 hour 15 minutes. I have on my lunch. Any more questions you would like to ask? If not, then we can break and come back.